Hello and welcome to section 11.5 today. Today we're going to take a deeper look at exponential functions. We started to look at some ideas of exponential functions yesterday, and today we're just going to look a little bit more um, at the specifics of the function itself. And then we're also going to tweak some of the other values and see what kind of differences that makes as we're getting through this. So let's go ahead and take a look. It says yesterday we started looking at exponential functions and their graphs, and we will formalize a method for graphing these functions today. So looking at it, the equation is f of x, or that's just a fancy way to say y. But we're dealing with y is equal to a times b to the x. And the important thing to realize is that with order of operations, only b is being raised to the x power. And here it says that b is, for this first one, that b is greater than 1. Now, it doesn't always have to be that a is greater than 0, but that's what both of these say. So we're going to kind of focus on that for just right now. The domain and range. The domain is all real numbers. You can put any number into this equation and it's going to work out. As far as numbers that you can get out of this equation when you plug numbers in, you have all the positive real numbers, so everything greater than 0 for a y value. The intercepts, it has one y-intercept and 0 x-intercepts because it doesn't really it doesn't cross the x-axis ever when it's just in this form. And then as far as end behavior goes, as x increases, the value of the function increases. And as x gets smaller and smaller, going this way, the graph gets closer and closer to 0. Okay. Now, pretty much the opposite's true if all I do is if I change b to b between 0 and 1. Okay, we won't deal with b being a negative value because that's going to do something weird. I might take a look at it, but it's going to do something weird as far as the graph goes. So same thing, really all the rest is the same except for the graph switches directions. Okay, this one we call exponential growth because as time goes on, if we think of the x-axis as time, as time goes, the population increases drastically. As time goes on exponential decay, the amount left, decreases, gets very close to, very close to 0. So let's graph all three of these on the same graph and see the differences that are going to come into play. I'm going to start with all of them at 0 because at 0, every single one of these is 1. I'm going to need different colors for these so that we can kind of keep them separated. So all of these are 1 when x is 0. When x is equal to 1, every one of these is just their value. So like this one is 1/3, this one is 1/2, this one is 2, and this one is 3. I said I needed different colors and I didn't use them. Perfect. So 1/2, 2, and 3. I'm working in the positive direction because that kind of works better in my mind anyways. For the next one, with all of them raised to the second power, that's just squaring all of them. When we square fractions, we get smaller fractions. So that's 1/9, that's 1/4, 2 to the second. Dang, I did it again, didn't I? See, I get math rolling in my brain and I forget patterns that I want to follow. 2 squared is 4, and 3 squared is 9. Okay, and then when I raise something to the third power, it gets even more extreme. 1 over 3 to the third power is 1/27. 1/2 to the third power is 1/8, and you can check all these with the calculator. I've I've worked with them enough now that I feel pretty confident there. Okay. Now, for the negatives, we dealt with these earlier, and these were the idea of flipping the fraction over. So we're going to see a lot of similarities in here in the numbers that we get. 1/3 to the negative 1 power is 3. 1/2 to the negative 1 power is 2. 2 to the negative 1 power is 1/2. And 3 to the negative 1 is 1/3. So you can kind of see the pattern that's going to evolve here. We have 9. How about 4? So like this is just this row flipped around. We have 1/4 and we have 1/9. And then the last one is going to be 27, 8, 1/8, and 1/27. All right, we're going to kind of generalize some of these because they get very small very fast. Like the first one, looking at the first column now, at -3, this is all the way up at 27. That's not even on my graph. So at -2, it's at 9. I can graph that one. At -1, it's 3. I can graph that one. And then at 1, it's 1. Or sorry, at 0, it's 1. At 1, it's 1/3. That's maybe there. Maybe a little bit lower. And then it goes, 1/9 and 1/27. So it gets very close, very, very close to 0. So I'm going to try to estimate the look of that graph as good as I can. It definitely doesn't come back up like that shows. And it's just going to trail off and get very, very close to 0 right in there. Okay, so that one is our 1/3 to the x power. For our next one, for our next trick, at 3 it's 8, so that actually will fit on my graph. At 2 it's 4. Sorry, at -3 it's 8. At -2 it's 4. At -1 it's 2. At 0 it's 1 again. 0, 1. At 1 it's 1/2. And then 1/4. And then 1/8. So that one's going to trail along like that. So we can again kind of try to, again, this is my worst direction of trying to graph when it's coming into my hand. I have a hard time with that. And then a lot of these are going to look pretty similar as we get out here because, they'd be at different points, but not much when we get fractions that small. This next one, kind of backwards from what we've done. At -3, it's 1/8, so that's probably in there somewhere. At -2, it's 1/4. I can do a little better there. At -1, it's 1/2. At 0, it's 1. At 1, it's 2. At 2, it's 4. And at 3, it's 8. So this one starts really close to 0. And it's coming down the line in some kind of a good pattern that I can't really draw at this scale. And then it gets very large very quickly. And the last one, same kind of deal. The important points, it hits 0, 1. It's going to hit -1, 1/3. So that would be a little bit lower than this one was. And a lot of the other times it's going to be lower. And then at 1, it's going to hit 3. So at 1, it hits 3. And at 2, it's going to hit 9. So a little bit accelerates, I would say, a little bit quicker than the previous one. It actually starts out below it. If there was any room there, eventually on our graph there wouldn't be any room. And then it accelerates much quicker. Okay. And so those are the four graphs that we get. Now, in the key concept up above, it mentions that A is a value being multiplied by B to the X. What effect do you think A has on the graph? Think about A being positive or negative, whole number or fraction. Okay. If we take all these numbers, so the idea of multiplying these functions by an A value would then take all these numbers that we have and multiply them by the same number. So just thinking with the first one here, if A was 2, well then it would be like 2 times 27, 2 times 9, 2 times 3, 2 times 1, and so on. 2 times 1/3, 2 times 1/9, 2 times 1/27. So I would say something along the lines if A was a positive whole number, well, if A was a positive whole number, that's going to kind of increase every single point. Every Y value would be increased. And I'm not going to do all of these, but I want you to think about what some other instances would be. It says that A has to be positive, and I would kind of argue against that. A doesn't necessarily have to be positive in any of these, but in order for them to be called exponential growth or decay, it would have to be. If A was instead of negative, and let's just think about a negative whole number, let's just think of it as -1. And I'm just going to write it on the second one just to see what I might get. And granted, -1 isn't that interesting. You could probably come up with something different, but it's going to make all these values negative. Okay, and I'm not going to write it out, but I'll kind of graph it here. On this one that was red, it would now look like this. Let's see, at -3, it's going to be -8, so it would look like something about like this as we would graph it. So it kind of flips it over the the x-axis. Okay, and actually gives us some of those negative numbers. So something to think about. Again, this isn't technically exponential decay like this one, like the red one was, but it's still an exponential function. Just doesn't fit that other mold. So dealing with that A value, let's look at this graph here, and I've got a better scale for this one. That's kind of nice. I'm going to look at 3 other ones. I'm going to look at y equals 2 to the x, y equals 2 times 2 to the x, and 3 times 2 to the x. So for kind of the base function here, the 2 to the x, 2 to the -3 is 1/8. I was going to say -8. That's not true. 1/8. 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. And 2 to the 3 is 8. Let's go ahead and graph that one while we've got it. Something we can work with. At -3, it's 1/8. At -2, it's 1/4. -1, it's 1/2. 1, 2, 4, and 8. So we have a much more zoomed in graph now. I know we've already graphed this one in particular, but it's kind of nice when you've got a scale that works out a little bit better with it. So we get a graph about here. And again, we're just doing our best. That's not any better. doing our best to make it a smooth curve, and this is true exponential growth. So I get something about like that. Not great, see if you can do better. For the next row, I'm just going to take all these and multiply them by 2. That's going to turn this into 1/4, turn this into 1/2. That's going to be 1. That's going to be 2, 4, 8, and 16. So it's going to really increase all these numbers. So we have 1/4, 1/2, 1, 2, 4, 8, and then I'll miss 16. It'll be way up there. So it's going to make the graph kind of take off in this direction. And pretend that actually went through that point. And it looks pretty good. Okay, and then if I take all these original ones and multiply them by 3, I don't know why I chose 3. Probably could have done something a little bit better. We'd have 3/8. We'd have 3/4. We'd have 1.5. I'm going to call it 1.5. I would have 3, and then 6, 12, and 24. So not many of those on the positive side are going to hit my graph, but that's okay. 3/8 is almost a half. 3/4 will be there. 1.5 there. 3 there. And then, 3 there, and then 6. And then I'm off my graph. So we see as we get a bigger and bigger A value, it's going to make our graph increase at a much quicker rate as we go. Okay. So now just taking a quick look at that idea of A being greater than 0 is not guaranteed. What do you think would happen if A was negative? We kind of already talked about this. Now, this didn't format very well, but this one would be y equals -2 times 4 to the x. And I didn't give us an XY chart here. I didn't give us a table of values, but we could kind of think about it step by step a little bit. And really all it's going to do is flip this over the x-axis. And we kind of talked about that already. But if I think about 4 to the x, at 0 it's going to be 1. And then I'm going to multiply that by -2. 1 times -2 is -2. 4 to the first power is 4 times -2 is -8. So at 1 it's -8. 4 to the second power is 16. 16 times -2 is -32. So at that point, we're all the way down there on our graph. And we can think about a couple numbers on the other side of y equals 0, x equals 0. If I think about -4 to the -1, 4 to the -1 is 1/4 times -2 is going to be -1/2. So that's going to be about there. And we're going to get -1/8 out of -2. So our graph would look a little bit more like this, which probably doesn't look too different from some of our other graphs today. But the scale is the big kind of determining factor here that shows us that there's a difference. Okay, if we were to scale this back to some of our other ones, we would really see a difference in the curve. It would probably be a lot sharper. We haven't dealt with 4 to the x yet. Looking at this next one, I have 1/2 to the x, which we've graphed. That was that original kind of decay graph, exponential decay. And so this one's going to be a lot similar. That if we plug in 0, we get 1, and 1 times -1 is -1. If we plug in 1, we get 1/2 times -1 is -1/2. and then 1/4, and then 1/8, and then 1/16. And those are all negative. Plugging in negative numbers, 1/2 to the -1 is 2, and then times -1 is -2, and then we get -4, and then -8, and then to the 4th, yeah, that would be like -16, so that would be off my graph. So, kind of take a look at what this graph's going to look like. A little inconsistency there. That's okay. I would have to flatten out just a little bit. There we go. Okay. But I really, out of this section, what I'm really looking for is that you develop some kind of a curiosity for what some different graphs do and what different numbers do to different graphs. Messing with this A value changes kind of the scale of the graph, but if it's negative, it can totally change it in that it flips it over. But really, it all kind of comes from that starting graph. What happened to that starting graph and how are these different? So anyways, if you have any questions, make sure you put them over on the left. Otherwise, have a great day and we'll see you in class.